In this video, we're going to go ahead and continue our conversation on logarithms by talking about how do we solve any exponential equation. Now, that's not necessarily true. There are some very advanced, and I mean extremely advanced, exponential equations that can only be solved using graphing utilities or computers. But we're basically going to talk about solving any exponential equation that can be solved using algebraic methods. So this is the end-all be-all for solving exponential equations. As a quick preview, I'll just let you know that we're going to do a review of properties of logarithms just using a basic example. And so these properties of logarithms, I have a lecture on them. It was the previous lecture I did, so please watch that if you're not up to speed on that. And then we'll go into some examples on solving exponential equations. We'll also use some natural base exponential equations as well, just to kind of get you used to that. So that'll be the newest thing for you here, but trust me, it's not really that new. You will need two prerequisites here. You'll need to know everything about exponential functions, how to kind of transform between exponential form and logarithmic form, and you'll need to know about logarithms and all their properties and stuff like that. So going into our first example here, just a review, this is more of an advanced review. Given that we have the log base b, in other words, we do not know the base here. All I know is that somebody's handing me some random base, not really random here, but some base b on these logarithms. Log base b of 4 is roughly equal to 0.71, and log base b of 9 is roughly equal to 1.13. Find log base b of 36 and log base b of 9/16. Honestly, you could actually find out what b is here. You could use a circular argument to say that b to the 0.71 power should equal to 4. You could do that, but let's actually use the given information to approximate these logarithms. Now remember, here's our properties of logarithms. We have a whole bunch of them, right? 7, 8 properties. The 8th one down here I have grayed out because that one, recall, is I rarely use. It's called the change of base formula, and generally you use it generally actually you use it in a textbook and that's it. But in real applications, you generally don't need to bother with using the 8th one. And actually in real applications, you rarely have to bother with dealing with the 5th and 6th properties as well. But the 7th property is the most important property of all. It is the kingpin property of all logarithms. It just basically says the most important property of logarithms, which is that logarithms unlock exponents. Okay, so we look through these properties here, and I noticed that I have nothing, well, I have a bunch that say log base b of something, log base b of something. Let's go back to our problem and see if we can determine which of those properties might help us. I have a log base b of 36, and I would like to rewrite that as something, and I see I have log base b of 4 and a log base b of 9. If you can kind of tell that log base b of 36 can be written as log base b of 4 times 9, which would link us back to these two logarithms they gave us. And I happen to know that log base b of 4 times 9, if you go back to our property here, log base b of m times n is a summation of their separate logarithms, log base b of m plus log base b of n. In other words, when you have multiplication going on the inside of your logarithm, you could split it as an addition on the outside. So that's log base b of 4 plus log base b of 9. So you're always looking for these properties if you can use them. And the reason why I chose to do that is because I happen to know roughly what log base b of 4 is, and I happen to know roughly what log base b of 9 is. So this is going to roughly, not exactly equal, but roughly equal 0.71 plus 1.13. If you add those up, you get 1.84. A little note on this notation that I'm kind of using here. A lot of students don't understand that I use equal signs sometimes, I use a approximate sign sometimes, and then I switch back to equal signs. Well, once you have an approximation sign within a chain of equalities here, that means that whatever happens after that point is approximately equal to your original statement. So this is really saying, since I started with log base b of 36, as I went through, I said equals, 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 and all of a sudden I had approximately. So from that point forward, I know whatever happens afterwards is approximately equal to. But it's approximately equal to 0.71 plus 1.13. And that is exactly equal to 1.84. But again, because we have an approximately equal to in between them, that means this whole thing is approximately equal to 1.84. That's just a little side note. So without using any type of calculator or anything like that, we easily found the value of log base b of 36, even though they didn't explicitly tell us anything about it. Now, log base b of 9/16 is a different story. I do have a log base b of 9, but I don't have a log base b of 16. However, you could write this as log base b of 9 over 4 squared. Now we have the 9 and the 4. Remember, when you have a division going on inside a logarithm, just like this property 6, we have a division, it is going to be a difference. The numerator will be the positive log, the denominator will have the minus sign in front of it, or it will be the negative logarithm. So we'll have this. This is equal to log base b of the numerator, which is 9, minus log base b of the denominator, which is 4 squared. Now this is still not good enough because I do not know what log base b of 4 squared is. I know what log base b of 4 is. So I go back to my properties. I'm hoping that I have a property that allows me to do something with that exponent. And I see the one that's highlighted here, which is the most important property of logarithms. That's the one that says I can pull exponents out front. Okay? As long as I have one object in there raised to a power, I can pull that power out front. So let's go ahead and do that. I'm going to go ahead and circle up this power, and I'm going to pull it out front of this logarithm. Not of all the logarithms, just the one that it's inside of. So this will become log base b of 9 minus 2 log base b of 4. Now I happen to know what log base b of 9 is and what log base b of 4 is, so I'll insert the values they've given me for those. That's going to actually not equal, that's going to roughly equal, because now we're inserting the rough approximate values. Log base b of 9 is roughly equal to 1.13 minus 2 of these log base b of 4s, which are 0.71. So that statement, now remember, I'm going to say that statement is equal to, because this statement actually is equal to 1.13 minus 2 of those 0.71s is 1.42. And that is equal to a negative 0.29. Now remember, it was a chain of equalities until I reached to this point, and it was an inequality. So, or it was an inexact equality, I should probably say. So therefore, when I say that log base b of 9/16 is related to negative 0.29, I can't say they're exactly equal because at some point I had their approximate. So this is approximately equal to negative 0.29. And that's how you do those style of problems, and that's a good review of our properties of logarithms. So let's get into solving exponential equations then. Here we have an equation, 5 to the x squared is equal to 16. Generally, if you are given an exponential equation, you start with something that might be easy. So you really look to see if these can be both represented by the same power. In other words, if it was 5 to the, and maybe I should write this in light gray so that I don't confuse you. Suppose for a moment that we were given this. If we're given 5 to the x squared is equal to 25, well, I know that 25 can instead be written as 5 squared. And now I can just compare their exponents. Okay, so you first try to look to see if their bases can be written as a power of, well, the same base. But in this case, 5 and 16 can't be written as powers of the same base. So that's pretty much out the window. And in fact, almost always that you're not going to be lucky enough to have that possibility. So, how do you solve something like this? Well, you use the properties of logarithms. Now, I'll tell you, most textbooks that I've seen ask you to take log, well, you could take the log base whatever you want of both sides. I could solve this by saying, let's go ahead and take the log, because remember, logs unlock exponents, and that's because of this property that I've highlighted here. I could take the log base b of both sides. It would unlock the exponent. If I do that, I could choose any base I want. So let's suppose for a moment, I'll put way 1. I'll give you 3 different ways you could do this. Let's suppose you said, I want to take the log base 3 of both sides. Okay, so just like squaring both sides, you're doing an action to both sides. Now, what was on the inside, or what was basically existing on both sides of the equation, was a 5x squared on the left-hand side and a 16 on the right-hand side. And now that we have this logarithm acting on both sides, we can use this wonderful property, the most important, right, to pull out the power on the left-hand side. So I'm going to grab this power on the left-hand side, and I'm going to pull it out front. Okay, so here we go. This will give us x squared times log base 3 of 5 is equal to log base 3 of 16. Now, one thing you have to remember is that these logarithms, once they're just numbers on the inside, like log base 3 of 16 and log base 3 of 5, those are just numbers. Log base 3 of 16 might be some number, oh, let's say 2.3, and log base 3 of 5 might be some number like 1.2 or whatever, but they're just some numbers. And so if I want to get x by itself, I would divide both sides by whatever this number is, this number right here. I'll divide both sides by that number. Okay, so here I go. I'm going to show you that division. I'll divide both sides by log base 3 of 5. Log base 3 of 5. And so on the left-hand side, log base 3 of 5, that picture over itself is just 1, right? A picture over itself is just 1. So we get the following. We get that x squared is equal to log base 3 of 16 over log base 3 of 5. Now remember, I want to solve for x, so I'm going to take the square root of both sides. Now recall our property that if x squared is equal to k, then x is equal to plus or minus the square root of k. So in this case, this implies that x will equal plus or minus the square root of the right-hand side. Log base 3 of 16 over log base 3 of 5. And that would be considered an exact answer. And that is absolutely correct. There's nothing wrong with doing it this first way. There's nothing wrong with it at all. That is perfectly correct. However, it's not the wisest approach. For one reason, if you open up your calculator, you'll see that you don't have a log base 3. You just have a log, which implies a log base 10. That's one reason why this is a really silly method to use. The other reason is it gives you an answer with 2 logarithms, which is not horrible. It's just, well, it's just not the best form. You could convert this into log base 10 if you want, but it's just a little extra work. Now, this is the method that not a lot of textbooks teach. However, the second method I'm going to teach here is going to be the method that almost every textbook I've seen teaches. And I still think the second method's not right as well. So the second method that most authors teach is they say, okay, look, we started with 5 raised to the x squared is equal to 16. So let's take the log of both sides again. By the way, all approaches to doing this, to solving an exponential equation from this point forward, will involve taking the logarithm of both sides, because that's what unlocks the exponents. But the base that they choose is going to be base 5. So I'll put a little 5 down here. And the reason why they choose base 5 is because, well, remember, the left-hand side was 5 to the x squared. The right-hand side was 16. Now let's take a look at this. Log base 5 of 5 to a power. If you look at our properties back here, log base b of b to a power is going to be just the power. So that means that if the base is equal to, if the base of the logarithm is equal to base of the exponent, that logarithm is going to just return the power. So log base 5 of 5 to the x squared is just going to return x squared, which is really nice. I mean, a lot of students love this method because it just looks cleaner, right? And now remember, I'm trying to solve for x squared, so I'll take the square root of both sides, and I get the x is equal to, remember, taking the square root of both sides implies a plus or a minus here. It's the property that when x squared is equal to a number, x is equal to plus or minus the square root of that number. But again, this is what most textbooks teach. But again, I go back to the fact that your calculator doesn't have a log base 5 button. It has a log base 10 button. This answer is still perfect. Don't get me wrong. This is a great answer if you're not trying to approximate a solution. But in real life, we tend to want to get an approximate solution to something. We want to know approximately what is x. And before I show you the third way, which is the way that I will commonly do these problems, I will just show you how to be able to convert these into a form where you can use your calculator. This grayed out property, the log base b of x, can be written as log base a of x over log base a of b, where a is any base you want that's positive and not equal to 1. So if I go ahead and think, okay, I need to approximate this, I could change this into log base whatever I want of 16 over log of that same base of 5. And if I'm going to use my calculator, I'm probably going to use base 10. So I could rewrite this as x equals plus or minus the square root of log base 10 of 16 over log base 10 of 5. Okay? So that is how you can convert that into a base 10, and then now you can grab your calculator and find out what that value is. In fact, I'm going to show you what that value is. I might as well, because we're going to use it in a moment anyway. So go ahead and grab your calculator. Remember, it's going to be the square root of log, remember once you hit the log button it implies base 10, of 16 and that logarithm, and divide that by log of 5. And recall, you have to close out this parenthesis and then close out the parenthesis for the square root. Hit enter. That's what the log of 16 over log of 5 is, square root of it, sorry. So that's roughly 1.31. So plus or minus, roughly plus or minus 1.31. Notice that I didn't do 16 divided by 5, right? You have to figure out what log of 16 is and then divide that by what log of 5 is. You cannot divide what's inside these functions. You have to evaluate each function first. Recall, it is just like using the order of operations, in fact. Remember, order of operations, when you want to calculate something, you work on the innermost parentheses, so that'd be this 16 or this 5. There's nothing I can do to clean up 16. There's nothing I can do to clean up 5. Then you hop outside parentheses, so that would be, now you're looking at the log of 16, and you let that go. So you figure out what that is. Same thing downstairs, you figure out what log of 5 is. Then you could do the division. Very important. Now let me show you the way I would normally do this. And I write my way here, but it's really a good standard way anyway. You'll see this in textbooks as well. What I do is I always, since I know I'm going to grab a calculator eventually to approximate this, I'm going to go ahead and take the log of both sides, like I did each time, but this time I'm just going to take log base 10. The reason why is because, well, listen, I'm going to have it in log base 10 to use a calculator, so why not just take log base 10 right now? The property of pulling out the exponents still is there. I can pull the x squared out front because it's a logarithm and it unlocks the exponents. So I still get x squared times log of 5 equals log of 16. I could now divide both sides by this picture, log of 5. So I get x squared is equal to log 16 over log of 5. And I'll take the square root of both sides. So that implies that x is equal to plus or minus the square root of log of 16 over log of 5. One thing I like about using this method, I don't have to use that change of base formula ever. If I just take log base 10 of both sides, I don't have to worry about converting to different bases later on. I could just go ahead and use log base 10 from the get-go. And notice that this answer right here is exactly the same as the answer we got using way number 2. But I didn't have to use an extra theorem. So it's actually pretty nice. It's a very nice method. And by the way, this is again roughly equal to a plus or minus 1.31. Okay, so that's how I'm going to solve this. My way business is how I'm going to solve the rest of these problems. I'm just going to always take log base 10. And I might later on, when I introduce the natural base, I might just show you, since you on your calculator you also have a different kind of logarithm base actually, I might use that also just to show you that there are two logarithmic bases that you could apply to both sides just as easily. They give you the same answers. But in this case, I'll stick with log base 10 for now, and I might go back through these problems and do a different base that exists on your calculator as well. The idea is to always just use a logarithm with a base that exists on your calculator, because that's what you're going to reach for eventually. Okay, example B, we have 15 times 2 raised to the 3x plus 12 is equal to 72. So the first thing you want to do is isolate your exponential expression. And just to show you that the method that I've been teaching this entire time with all my lecture series, from the very first lecture when I talk about how to solve equations, I've said if you only have one version of your variable, in other words there's only one x in this entire equation, you can just untie, quote unquote, untie the knot. Which means I always start these saying, what happened to x? And I love just doing this every once in a while, so just to show you that this old school method of just asking yourself what happened to x is useful for any kind of equation. As long as you have one version of your variable, you can use this method, the untying method, to solve any equation you want. So in this case, if you just zoom into x here, the first thing that happens to it following the order of operations based around x here is it gets multiplied by 3. After it gets multiplied by 3, somebody goes along and adds 12 to it. Again, this is, as I've described in the past, when you're given an equation and x is just tied up in a bunch of numbers, it's like somebody's hiding the value of x from you. They don't want you to know what x is, and it's your job to undo all that. So after they've multiplied by 3 and then added 12 to it, the next thing they did is they raised it base 2. So 2 to the whatever it is. Okay, so they've raised it base 2. After they've done that, they've multiplied it by 15. That's all the stuff that they did to hide the value of x from me. That's like tying up x into a knot. And how do you untie a knot? Well, you undo each thing that they did, starting with the last thing. Right? So you untie this last knot first. So I'm going to do the inverse of multiplication, which is division by 15. I'm going to do the inverse of raising to the power to base 2, which is take a logarithm, and I know it normally should be logarithm base 2, but I'm always going to use logarithm base 10 in my problems. But you could do logarithm base 2 if you want. Next thing I'm going to do is untie their addition by 12 by subtracting by 12. Finally, I'm going to undo their multiplication by 3 by dividing by 3. So I could easily create a roadmap of operations to follow. If I start by dividing both sides by 15, I will get, let's see, implies, dividing both sides by 15, I get 2 raised to the 3x plus 12. Remember, dividing both sides by 15 means that if you have a factor of 15 on the left-hand side, they cancel. 15 over 15 will become 1. And then 72 over 15, that reduces slightly. 3 goes both into the numerator and the denominator, 24 over 5. So that's what the ratio will turn into. Not that I actually have to do that, because I'm going to be reaching for a calculator eventually, I know that. But I just thought I'd do it anyway. So that step is done. Now I tell myself I'm going to take the log base 10 of both sides. I know you might want to do the log base 2. You're more than welcome to. But I like the log base 10 because then I don't have to do a change of base formula. Now the one thing the logarithm I was going to say base 10, but logarithm base anything allows me to do is it allows me to grab that entire exponent. Remember, it grabs the entire exponent, not just part of it. It grabs the entire exponent and throws it out front. So let's go ahead and rewrite this with that exponent written out front. Now that exponent is this picture, 3x plus 12. Okay, so times log of 2 equals log of 24 fifths. Well, this is something that's not accounted for in my list of steps here. The thing that's not accounted for is the fact that once I am able to pull that logarithm or that exponent out of the logarithm, I have this number, log of 2, that's multiplying this picture. So it's a little bit of a flaw in this inverse step terminology. But just know that when you take the log of both sides, the exponent can flip out front, and you could divide both sides by that remaining logarithm. So I'm going to divide both sides by log of 2 here. And maybe I should be explicit here. I'm dividing both sides by log of 2. And on the left-hand side, I can cancel like factors. Log of 2 looks just like log of 2, so that's going to be the number 1 there. On the right-hand side, that's just going to be that mess. So this implies that I have 3x plus 12 is equal to log of 24 fifths over log of 2. And remember, I don't divide 2 into 24 fifths. I can't do that. Because if you think about the order of operations, the order of operations would say figure out what 24 fifths is first, and then figure out what log of that is second. Same thing downstairs. I would figure out what log of 2 is first. Then I would do the division. So you can't divide the numbers. You have to figure out what the logs of those things are first, which I'm not going to bother with even. All right. So I'm done with taking the logarithm of both sides and kind of cleaning that up. The next thing I will do is subtract 12 from both sides. So this will give me that 3x is equal to that nastiness, which is log of 24 fifths over log of 2, and then minus 12. And now I'll divide both sides by 3 to get that x is equal to. Now dividing by 3 is the same thing as multiplying each denominator by 3. So that's going to be like log of 24 fifths over 3 log of 2 minus 12 over 3, or in other words, 4. That would be our exact answer, and that's generally what an instructor might want on an exam, an exact answer like this. And that's what I would like on an exam. However, I would also like to see that you could possibly use your calculator. So let's go ahead and calculate this and round the answer to the nearest hundredth, let's say. So I'll bring up my graphing calculator here, and you could use a scientific for this as well. And we'll type in log of 24/5 and that logarithm divided by. Now, since we have some arithmetic going on down here, I'm going to have to put in a parenthesis. 3 times log of 2 and that logarithm and that denominator. And then finally, minus 4. Negative 3.25. Negative 3.25. So what happened to X business can be used all throughout mathematics. The only kind of wonky issue with it is that when you do that log base 10 on both sides, there are some additional little implied steps. One, that you pull out the exponent, and two, that you divide by that remaining logarithm. Let's try another one, and we'll do this very quickly. So 801 is equal to 20 times 3 raised to the negative 0.6x. I'm just going to list out what happened to x here. The first thing that happened to x is it got multiplied by a negative 0.6. The next thing that happened to x is it was raised base 3. The next thing that happens is it gets multiplied by 20. So I'm going to undo each of these, untie the knot, by dividing both sides by 20 first. Then by taking a logarithm of both sides, log base 10 I'll do, but you could do log base 3 if you want. And then finally, I'm going to go ahead and divide both sides by negative 0.6. Now remember, when you take the log base 10 of both sides, there are some implied operations that must go on here. So just to let you know that you have to take out exponents and kind of divide both sides by the remaining log at that point, which we'll see. So I'll divide both sides by 20 first. And you see on the right hand side, 20 over 20, those factors cancel. They become 1. So this implies that we have 801 over 20 is equal to 3 raised to the negative 0.6x. And now I tell myself, okay, I got to take the log base 10 of both sides because that will unlock the exponent. So I'll take log 801 over 20 equals log of 3 raised to the negative 0.6x. At this point, a lot of students tend to just immediately throw the exponent out front. I'm absolutely okay with that. Instead of rewriting it like this, they automatically just rewrite it with the exponent out front. I think that's perfectly fine. In a lecture, I tend to be more loquacious, which means wordy. Okay, so I'm just pulling this exponent out front here, negative 0.6x times the log of 3. And remember, one more implied operation here is once I pull out the exponent, I'm going to divide both sides by log of 3. Even though that's not in my list of things to do there, I'm going to do it. Log of 3, both sides. And you see on the right hand side, log of 3 is both a factor in the numerator and denominator. So log of 3 over log 3 turns into 1. So we get the following. Log of 801 over 20 divided by log of 3 must equal negative 0.6x. Now I get to divide both sides by a negative 0.6x. Or negative 0.6. Not x, but negative 0.6. Now remember, dividing by a negative 0.6 is the same thing as multiplying the denominator by a negative 0.6. On the right hand side we'll get x. On the left hand side we will have a negative, a log of 801 over 20 over 0.6 log of 3. I just pulled the negative out front, that's all. And now to find out what this x value is, I'll just bring up a calculator. I have it in base 10 already because, well, That helps out quite a bit. I'll type in negative, remember not the minus sign, but the negative sign, log 801 over 20, close out the logarithm, and divide that logarithm by, well, I have some arithmetic going on in the denominator, so I'll have to start a parenthesis, 0.6 times log of 3. Close out the log, close out the denominator, hit enter, and we'll round to the nearest hundredth again, so this will be negative 5.60. So x is roughly equal to a negative 5.60. Little note on that rounding there. Notice that I wrote 5.60, negative 5.60, rather than negative 5.6. I'm just telling the world that I have rounded it to the nearest thousandth, or hundredth, I'm sorry, by making sure I write in the 0. That way anybody that looks at this will say, oh, he rounded to the nearest hundredth there. That's why he has a 0 in there. If I said negative 5.6, people might think I rounded to the nearest tenth, which will tell them that I'm being less exact. This is a little note you might want to take advantage of when you reach chemistry, physics, anything like that. You want to make sure that you're rounding, even if you have zeros at the end, that your rounding includes those zeros, so that you tell whoever has that number later on that that number is very exact. Now I've decided to kind of go back to this the very first example we did here, because I had mentioned a moment ago, or a few minutes ago, that there is another base that your graphing calculator has, or that your scientific calculator has. I'm opening up mine right here, and if you look, I have a log, which means base 10, and then I have this thing that says ln. Essentially, ln is just a logarithm with a certain base. Just like log base 2 has a base of 2, and log base 3 has a base of 3, log base 2.718 ... of x is the same thing as log base, well, that 2.718 ... is a very special number, and that number we call e. I'll show you. E to the first power on your calculator will be 2.718281828 4545 something 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 something. So this is the same thing as saying log base e. Okay, that's just a special number, just like pi is a special number. 2.7182818284545. It's, or I think it's 459045. Anyway, it goes on forever, just like pi does. But anyway, that number that we call e is just a very special number. For now, just know it as a very special number. So e is roughly equal to 2.718281828. I'm almost positive it's like 459045. You know what? I shouldn't write it down unless I'm positive that it's that. But I did just check it, and that is how it expands out. So that is a very approximate version of e, but a pretty good approximate version of e right there. Anyhow, it's a very special number. And by the way, log base e, just like log base 10, log base 10 of x, we call that the common log. So it happens so commonly that we just drop the 10, and it's just log of x. Okay. Well, log base e is also a logarithm that happens a lot. In fact, in the natural sciences, it happens very, very often. And so we call it the natural logarithm. The natural logarithm. And the special notation we use for that is ln, for log natural. I don't know if that's really what I think it does, but actually mean logarithm natural. So it must be French, right? ln. ln of x is the same thing as saying log base e of x. It's not that big of a deal, really. Don't get all freaked out when you see an ln. It just means you could rewrite it as log base e if you want to. That's what I initially did when I was in learning mathematics. So let's go ahead and just solve this problem again, but using the natural log, just to show you that it can work just as well as the common log, which is log base 10. So when I go to solve this, I'll take the log of both sides, but this time I'll just show you. I'm going to take the natural log of both sides. A lot of people really at this point go, what is going on? Oh my goodness. But remember, this notation is the same thing as saying log base e, where e is just 2 point whatever, 2.71828, da 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 da. So log base e. Now, because it's a logarithm, it has all the properties of a logarithm. It takes that exponent, throws it out front. So this implies x squared times log base e, if you want to write it that way, of 5 must equal log base e of 16. I'll tell you, actually, the only strength of taking the natural log in this case is that it's actually faster to write. If you don't write log base e and instead you write ln, it's much faster to write. But again, log base e of 5 is just some number. I'm going to divide both sides by it. So divide both sides by log base e, or in other words, natural log of 5, the natural logarithm of 5. On the left-hand side, those pictures will cancel, the same factors. So you get that x squared is equal to, and now I'm just going to write as ln of 16 over ln of 5. I'm tired of writing log base e. It means ln. Okay. And now I'll take the square root of both sides. That tells me that x is equal to plus or minus the square root of ln of 16 over ln of 5. Now, let's see if this is exactly the same as our first example that we gave here. Remember, in the first example, we had log of 16 over log of 5, and it ended up being a plus or minus 1.31. In this example, instead of using the log, I'm going to use the ln on my calculator. So I'll take the square root of ln, meaning natural log of 16, again, close the parentheses, divided by the natural log of 5. Close parenthesis for the natural logarithm, close parenthesis for the square root, hit enter, and there we are, 1.31 again. So this is still plus or minus 1.31. So I guess what I should be saying is you could take the log base 10 of both sides, or you could take the natural log of both sides. It doesn't really matter. Remember, natural log is just log base e, where e is just 2.71828, all that fun stuff. It's just a different base. But all the mathematics are exactly the same. Now, as a final example, we're going to go ahead and solve this equation for t. So I want to get t by itself. Now, the statement I made a while back about writing out what happened to t, or listing out what happened to your variable, is so much more important when you're doing a problem like this, where you have a lot of letters involved, because I think this is where students get completely flabbergasted. So list out what happened to t. Just focus in on t here and ask yourself, what was the first thing that happened to it? Well, it got multiplied by k. I see that. The second thing that happened to it after it got multiplied by k is it got raised to by base 10. The third thing that happened to it after it became 10k to the kt is they subtracted 1 from it. After that, when they had 10 to the kt minus 1, they multiplied all that by a naught. So now that helps me build a roadmap. I'm going to untile the stuff that they did. So the first thing I'm going to do is divide by a naught. Second thing I'm going to do is add 1. Third thing I'm going to do is take the logarithm of both sides, base 10. And the fourth thing I'm going to do is divide by k. So let's go ahead and start that. First thing I'm going to do is divide by a naught. So here we are, a naught, a naught. On the right hand side, those pictures are exactly the same, so I get to cancel them. On the left hand side, they're not exactly the same, so they don't cancel. They just are rewritten as a over a naught. And that equals 10 to the kt minus 1. So that takes care of that step. The next step says add 1 to both sides. I'm not going to show me adding 1 to both sides. I'm just going to do it. So that's a over a naught and then plus 1 on that side is equal to 10 to the kt, and that minus 1 has been taken care of because I added 1 to it. Next step that I say I have to do is take the log base 10 of both sides, which does a little bit of magic in this case. So I'll take the log base 10 of both sides, it's a over a naught here, plus 1, equals log, again, base 10 of 10 to the kt. Well, this one's kind of nice. If you didn't notice, by the way, that log base 10 of 10, these two things, when you have the log base 10 of 10 to the kt, this whole thing will turn into the kt. But if you hadn't noticed that, you could still kind of say, okay, that rips out the exponent, pops it out front. So you could still take your time doing this, and you'll see it in a moment. This will be log of a over a naught plus 1 is equal to kt times log of 10. But log of 10, this business right here, log base 10 of 10, is equal to 1. So really, that shouldn't even be there. It's just 1. It's the number 1. And now the last thing, so that's done. The last thing I need to do is divide both sides by k. On the right hand side, the k's cancel, and I will get t is equal to log of a over a naught plus 1 all over k. And that is your final answer. Whoops, didn't mean to go through my k there. Anyway, yeah, so that's how that problem is done. Now, I want to make sure that you're okay with the natural logarithm thing that I just mentioned a moment ago. So maybe I'll do one last problem here, because even though I told you that this was the last problem. Suppose I have this exponential equation, and this base e is not a variable. Remember, e is roughly equal to 2.71828 9045, and it goes on forever, just like pi. Okay, so this is just some number, a horrible number, but it's some number. Now, what I'm going to do is start to solve this for x. So let me list out what happened to x here. First thing that happened to x is it got multiplied by 0.3. Second thing that happened to x is it got raised to, base by base e. Third thing that happened to x got multiplied by 20, and then finally they subtracted 1.8 from it. So I'm going to undo all of their operations in reverse order. So instead of subtracting by 1.8, I'm going to add 1.8. Instead of multiplying by 20, I'm going to divide by 20. Instead of raising base e, I'm going to take the natural log of both sides. The reason why is once I see an e in a problem, I know I need to do a natural log. Because remember, the natural log is just log base e. Okay, that is the same thing as saying log base e. That will help out quite a bit. And finally, instead of multiplying by 0.3, we're going to divide by 0.3. So let's go ahead and do this. If I add 1.8 to both sides, I will get, what is that, 8.2 is equal to 20e to the 0.3x. Now I will divide both sides by 20, and just do that. Divided by 20, divided by 20. It is your choice if you want to actually do that division right now with a calculator, but I personally don't want to even touch a calculator until I get to a very final answer. Just a good habit to get into, because otherwise you really risk rounding incorrectly your answers. Now we're at this point here, and I tell myself, by the way, I'm done with those two, I tell myself to take the natural log of both sides. So I'm going to take the natural log of the left-hand side of 8.2 over 20, and the natural log of the right-hand side, 0.3x. Now remember, a logarithm, which is what this is, it doesn't say explicitly log, does it? But ln is log of base e. So if you need to write that in, you can. But I know it's a logarithm, so I know that it's going to wrap up this exponent and rip it out front. It allows me to unlock that exponent. So I'll go ahead and write this as the natural log of 8.2 over 20 is equal to 0.3x times the natural log of e. Now let me show you something about that natural log of e business. That is log base e, right? That's the natural log of e. Well, we have a theorem way back when. Log base b of b, that's just 1. So log base e of e must be 1. So this business right here is 1. So this is actually equal to just a 0.3x on the right hand side. Let me go ahead and just take that out. So now I've gotten rid of all exponents in the problem. Now I can just divide both sides by 0.3. When I do that, I get that x is equal to that natural log of 8.2 over 20 being divided by a 0.3. And I can reach for my graphing calculator. And I'll take the natural log of 8.2 over 20, and I'll divide that by 0.3. Negative 2.97 roughly equals negative 2.97. So it's just a heads up on natural logarithms and how to use them. They work just like regular logs. They are regular logs. You should not feel like they're any different. They're not. It's just that your calculator only does 2 logarithms, one base e and one base 10.